In this section, we will consider sums over Poisson processes. More precisely, we will study random variable sigma of the form given by the sum of function f of x, where x are points in some Poisson point process pi. Okay, so namely this pi is a Poisson point process with some mean measure mu on some measure space S, and f is a measurable function on this space. And we will study two questions here. So first, when this sigma is well defined, or more precisely, since the points in our process do not come in any particular order, when the series is absolutely convergent with probability 1. And number 2, we will also compute either Laplace transform or characteristic function of this random variable. Now, we will notice right away is that if we consider a set where our function is strictly positive and another set where our function is strictly negative, the intersection of our Poisson process with these two sets results in two independent Poisson processes with the measure mu just restricted to those sets. Okay, that's by the properties that we proved in the previous section. Particularly, this means that if we let f plus to be the positive part of our function f and f minus be the negative part, so minus this minimum of f and 0, and if we consider the random variable sigma with either index plus or minus given by the same sum as above, just of positive or negative part of f, then our original sum can be represented as sigma plus minus sigma minus, assuming that the series is absolutely summable, and moreover, these are independent. And so it's enough to answer the questions above for sigma plus or sigma minus, or in other words, we can assume from the very beginning that our function is non-negative, and for the general case, we'll simply combine the characterizations for the positive and negative part. So for now, let's simply suppose that f is non-negative and consider this random variable given by the sum over points in the Poisson point process of function f of x. In other words, it's a non-negative random variable. Now we know that the distribution of a non-negative random variable can be characterized by its Laplace transform, expectation e to the minus t sigma for non-negative t. Okay, of course, this comes from the fact that if we consider a function phi of z, which is the expectation of e to the z sigma on the complex plane, okay, in the case when sigma is a non-negative random variable, one can easily check that this is holomorphic on a half plane when the real part of z is strictly negative. Okay, and that's just because you have integrability conditions to interchange derivatives and integrals, which will allow you to check the Cauchy-Riemann equations. And at the same time, the Laplace transform gives you the values on the negative real line, and so that means that it determines this function phi of z by continuity on the half plane, including the imaginary line. So it determines uniquely the characteristic function, and as a result, it determines the distribution. And our first main result will be, in this case of non-negative function f, namely the following theorem, which is called Campbell's theorem, and this will be part 1 of it for non-negative random variables. So in the case when our function is non-negative, we'll prove the following statements. So first, we will calculate the Laplace transform above, and we'll see that it will be given by exponential of minus the integral of 1 minus e to the minus t f of x with respect to our mean measure mu of x, okay, for all non-negative t. Part 2 will show that our series is finite almost surely if and only if the integral of the function f of x truncated at 1 with respect to the mean measure is finite. And also one can compute the expectation of this random variable as the integral of f of x with respect to the mean measure. And if the expectation exists, one can compute the variance as the integral of the square of this function with respect to the mean measure. Okay, where these two equations are understood as equalities either finite or infinite. So if one side is finite, another side is finite, and they are equal, and so on. And moreover, when we write the statement about variance, we assume here that the expectation is already well defined. Now, the second statement about almost sure convergence, it can be proved in exactly the same way as we handled an example at the end of the last section. Okay, but here we'll prove it in a slightly different way. And we begin with the first statement. So first we will consider the case when the function f is a step function. So if f is a step function, let's say it takes the following particular form. So f of x is a finite sum of some values f of j on the indicator of some measurable set aj, and here we'll take these aj to be disjoint. Okay, then for such function it's very straightforward to check the statement of our theorem. Okay, because we can represent this random variable sigma given by the sum over all points in our process of f of x, that we can simply sum over j the value f of j times the cardinality of our Poisson process inside the set aj. And we know that these are independent Poisson, and the mean of each Poisson is just the measure of the set aj. So as a result, when we compute the Laplace transform of this random variable, we can write this as, by independence, as a product over j, expectation of e to the minus t fj times this Poisson random variable aj. And here we just have to recall what the moment generating function or Laplace transform is for the Poisson random variable. Right? Namely, if you take a Poisson random variable n and we want to compute expectation of e to the xn, just by definition it will be sum over all integer values e to the xk times the Poisson probability. So if the mean is lambda, this will be lambda to the k over k factorial e to the minus lambda. Right, and we can see that this is just e to the minus lambda times the series for the exponential evaluated at lambda e to the x. So if we use this formula for each factor in the above product, we get e to the minus mu of aj plus mu of aj e to the minus t f of j. Okay, and this is exactly e to the minus the integral of 1 minus e to the minus t f of x with respect to the measure mu x, under this assumption that function f is a step function. So in other words, we get this equation that we want for the Laplace transform of our random variable sigma in the case when f is a step function. Now, in the general case, we can now simply approximate by a sequence of step functions. In fact, monotone sequence. So we can take a sequence of step functions as above, which is monotone and converges to our function f. Now, first of all, when we take a look at the left-hand side of this equation, okay, so we can see that in this case, if you take sigma n to be the same sum over our Poisson point process of fn of x, this will converge monotonically to sigma given by the original sum. Right? And that's of course because all our functions here are non-negative. So for non-negative series, you can interchange the limit and the summation. And so as a result, the expectation of e to the minus t sigma n will converge to the expectation or Laplace transform of sigma just by the monotone convergence theorem. And the same on the left-hand side, right? When you consider the integral with respect to the measure mu, here if you replace f by f of n, again for any non-negative t, the integrand will converge monotonically. So this whole integral will converge to the same integral for f of x for any non-negative t. Okay, and so as a result, the above equation for step functions immediately implies the same equation for any non-negative function. So this proves part 1. Now if you want to prove part 3, I'm going to skip it here because it's exactly the same as part 1. Because you can easily check that for a step function, both equations for the expectation and for the variance hold, and then everything else follows by monotone convergence theorem. And then finally, part 2, we want to check when this series converges almost surely. Namely, we want to show that this is if and only if when the truncation of our function at 1, when you integrate it with respect to the mean measure, this converges. Now this can be done, as I said, as in the example in the previous section, but here we can also derive it directly from the formula for the Laplace transform. And for this we just have to notice that if we look at this integral in the Laplace transform here, then the condition on the right hand side here is actually equivalent to the condition that the integral in the definition of Laplace transform is finite for any fixed positive t, or automatically it will be true for all t. Okay, and of course the reason for this equivalence on the right hand side is because the integrands are in some sense equivalent. If you consider when the function f is less than or equal than 1, then 1 minus e to the minus t of f of x, well, it's basically of order tf of x. And when f is bigger than 1, then this integrand, well, it's in between 1 minus e to the minus t and 1. So it's like a constant. Right, and so on both sets our integrands are equivalent, so both integrals on the right hand side here either converge or diverge at the same time for any fixed t. And so now we can just consider two possibilities here. So the first possibility is when this integral is actually infinite. So if the integral is equal to plus infinity for some positive, but at the same time it means for all positive t, By part 1, that means that the Laplace transform is equal to e to the minus this integral, so actually it's equal to 0. But in this case, of course, it means that the random variable sigma is plus infinity with probability 1. So there is no weight on the set where sigma is not plus infinity. And in the second case, if we suppose that this integral is finite for any fixed t or for all positive t, then we will simply consider t in between 0 and 1, and in fact we will let t go to 0 monotonically. And we will use the fact here that the integrand for t less than 1 will be bounded by the same integrand for t equals to 1. So we will have this function that dominates all t and is also integrable. So by dominated convergence theorem, when we let t go to 0, what we get is that this integral here converges to the integral of 0, so it converges to 0, and as a result, the right-hand side of the Laplace transform equation, the exponential, converges to 1, and on the other side of the equation, we can see that e to the minus t sigma, this will converge when t goes to 0 to the probability when sigma is finite, right? Because on the event when sigma is infinite, this exponential is just 0 for all positive t, and otherwise this exponential will go to 1, and so you get this convergence here again by monotone convergence theorem. Okay, so in other words, we proved that this probability is equal to 1, and this finishes the proof of part 2 and the proof of this Campbell's theorem in the case when our function f is non-negative. Now from here we can immediately derive the general case, so the Campbell's theorem in the general case, namely when the function f is not necessarily positive or negative, so when we can decompose it into a positive part and a negative part, and in particular we in this case also decompose the series into the positive part and the negative part. And so if you apply the above theorem for the positive to this difference, then automatically you get the following three statements. And I'm going to change the order of the first and the second. So first we'll say that the series is absolutely convergent, which of course means that the series sigma plus and sigma minus are both finite almost surely if and only if the integral of the truncation of the absolute value of f at 1 with respect to the mean measure is finite. So we know that the convergence for the positive and negative part just means that this truncation is convergent for both the positive and negative part of f, and so that's exactly this condition here. Now, when f is neither positive or negative, the Laplace transform may be undefined, so here we write the characteristic function. And so the formula for the characteristic function will be very similar. It will be exponential of the integral of e to the it f of x minus 1 with respect to the mean measure mu of x. Okay, and the last one is that the same formulas will hold as above. So the expectation of sigma is integral of f of x, where we of course mean that these integrals are defined when the functions are absolutely integrable. So in other words, the expectation of the absolute value is finite if and only if the integral of the absolute value here is finite. And again, if the expectation is defined, then the formula for the variance is the integral of f of x squared with respect to the mean measure, where two sides are either finite or infinite at the same time. But this statement assumes that the expectation is well defined. Right, and all the parts follow from the above theorem, and so maybe we just have to say one word about the second statement about characteristic function, where basically when we write our sigma as sigma plus minus sigma minus, we compute the corresponding Laplace transform for the sigma plus and sigma minus, which was given by this exponential. I'm just going to switch the sign in the integral, so we wrote it slightly differently above. So here, positive or negative part. Okay, and as we said above, once you have the Laplace transform, you also have the same formula holds for the case if minus t is replaced by a complex number z, when the real part of z is less than or equal than 0. Okay, just because both sides are analytic on the set where real part is strictly less than 0 because our functions are non-negative, and then by continuity we can also extend it to the imaginary line, and so the same formula holds for the characteristic function, and then using the independence of this plus and minus, putting the two together, right, gives us this formula in the statement number 2. And so the case for positive functions immediately implies this more general case for signed functions f. The only difference is that we have to work with the characteristic function instead of Laplace transform in this case. And so this formula for the characteristic function of the sum over a Poisson process characterizes the distribution in terms of the mean measure and the function f, okay, which will be useful to us in later sections.